Right. Good afternoon, everybody. Before we continue with rotational motion, there are two practicals involved. Practical number 5 and practical number 6, which is connected to equilibrium section. So we'll finish that and move forward. Is it clear? Right. Practical number 5. Practical number 5. Right topic. Finding an unknown mass. Finding an unknown mass. Finding an unknown mass using the principle of parallelogram of forces. Using the principle of parallelogram of forces. Finding an unknown mass using principle of parallelogram of force. Some people say law of parallelogram of force as well. No problem. What do you mean by parallelogram law? Parallelogram law. Right. If two forces are represented, look at this carefully, concentrate. If two forces are represented on adjacent sides of a parallelogram, if two forces are represented on adjacent sides of a parallelogram, you have done this. Where have you done this? R squared equal P squared Q squared 2PQ cos theta, you remember? Same thing. If two forces are represented on adjacent sides of a parallelogram, the main diagonal will give you the result. There. The main diagonal will give you the result. You remember? Here a force, here a force. Where is your resultant? Through the center. Is it clear? Through the center. So here, if you complete the parallelogram, here you go. The main diagonal will give you the result. The main diagonal will give you the result. So here you have vector P, here you have vector P, Q, this will be the result. Okay, no? That's right. That's right. If two forces, this is a theory, you can write on side, theory. This is the theory. If two forces are represented, on adjacent sides of a parallelogram, if two forces are represented on adjacent sides of a parallelogram, the main diagonal will give us the resultant. The main diagonal will give us the resultant. The main diagonal will give us the result. Okay, right. Quickly draw this in. So P and Q are the forces. R is your resultant. R is the resultant. P and Q are the forces. P and Q are the forces. R is the result. Right, no? So today what we are trying to do is very simple. First I'll teach the whole practical on the board. Then I'll show you the video. Okay? So what we are trying to do is, we'll try to use two forces and there'll be a resultant. Yeah. So our lesson is equilibrium. This resultant here, I can balance it by equal opposite force. Yeah. Understood? So there are two forces which will give you a resultant. Resultant means object will go in that direction. How can I balance it? There will be an equal opposite force acting in the opposite direction. Okay, no? So this is the theory. Two vectors acting, or if there are two forces on adjacent sides of a parallelogram, the main diagonal will give us the resultant. Okay, right. Right. Apparatus needed. Apparatus needed. Under that, right, first one, an unknown mass. An unknown mass. Set of weights. Set of weights. Set of weights. Set square or plane mirror. Set square or plane mirror. Set square or plane mirror. Half meter ruler. Half meter ruler. White A4 sheet paper. White A4 sheet paper. Comma. Triple beam balance. Triple beam balance. Triple beam balance. Comma. Parallelogram of forces apparatus. Parallelogram of forces apparatus. Parallelogram of forces apparatus. Right. Look at the word carefully. This is your procedure. This is your procedure. I will show it point by point. Now, parallelogram apparatus means there is a boarded, or there's a flat board. Flat board connected to the wall. Flat board connected to the wall. What we do is, we place two pulleys such that their centers are in line with each other. So remember, parallelogram of forces apparatus, that means they are talking about the pulleys, they are talking about the board, everything. But remember, there will be two pulleys. Our job is to make sure that the centers are in line. If the centers are not in line, then what? There's going to be a problem when you do the experiment. So make sure that the centers of the pulley are what? First in line. Once the pulleys are in line, then what you do is, you take a string, cotton string, send it over the pulleys, send it over the pulleys. And then what you do is, you connect it to a known weight. Connect it to a known weight. Now remember, there will be scale pans. Here these are your scale pans. Some people draw it like that. These are your scale pans. These also have weight to propagate. On this we put two known weights. On this we put two known weights. Okay, no? Then what do we do? Now these are known weights. For example, I'll take an example, basic example. I'll take this as grams. I'll take this as 50 grams. I don't know, 50 grams. Okay. So the weight is 40 grams, scale pan, separate weight. Weight added here 50 grams, scale pan, separate weight. Make sure that the scale pans all have the same weight. So it's easy for you to identify. Now you can see the thread like this. Now what to do is, I'm drawing the next picture. What you should do, somewhere around the center, we connect it to another known weight. Right? Before you do the experiment and find the unknown mass, you have to check whether parallelogram of forces is what? Correct. Understood? So what you're doing first is we are using known weights. I'll show you the concept. Here known weight, here known weight. Centers are in line. Then what we do is somewhere around the center, we hang another known weight. Somewhere around the center, we hang another known weight. So pulleys are in line with each other. Pulleys are in line with each other. Here you go. Pulleys are in line with each other. Somewhere around the center, we hang another weight, means here you go. The string will come like this. Strings are vertical, don't forget. Strings are vertical, don't forget. And that is connected to your known weights. That is connected to your known weights. Here we connect another known weight. Let's say the weight there is around 40, 50. Let's say known weight there around 60 grams. Here 50 grams. Here 40 grams. So these is known. Now, once you get it here, what we do is, somewhere here using drawing pins, we fix the A4 sheet. We fix the A4 sheet. Here, you fix the A4 sheet to this wooden board. So the A4 sheet is behind here, don't forget. The A4 sheet is behind here like this. Fixed to the wooden board. Right. Please remember, none of the components are touching this board. If I draw it from the side for you all to see, from the side if I draw it, board is there, pulley is there, string is passing over the pulley, connected to the weight. So is the string touching the board? No. Is the weight touching the board? No. There is no touching there. Because if it touches, there will be what? Friction. So they are free to move. They are free to move. So this is your initial apparatus. Once you set this up, what you do is just to check whether there is friction. Just to check whether there is friction. Please look at the center where this Y shape is formed. We pull the weight, center weight slightly and release it. You can pull any weight. Pull the center weights because this Y shape is there. You know the point. Pull the center weight slightly down, release it. If this point comes down and goes back again to the same state, we say no friction in the pulleys. If I pull it down, this point comes, doesn't go back to the starting point. We say what? There is friction in the pulleys. What can you do about it? Nothing. You just know that there is friction in the pulleys. There. That you can use it as an observation in your practice. Understood? If you are given some oil, then you can put some oil on the pulleys to make sure there is a lesser friction. Is it clear? There is lesser friction. Right. So what's your first job? Connect the apparatus so that the pulleys are in line with each other. Fix a A4 sheet of paper, send a string over the pulleys, put two known weights. Exactly at the center of the rope, we connect another known weight. And to check if there is friction in the pulleys, we pull the center weight down and release it. If the Y-shape point or Y point here, you can see the Y or junction point there, goes back again to the starting point, we say there is no friction. But if it doesn't go back to the starting point, we say what there is. Once you reach here now, look at this carefully. There are mainly two methods where you solve the problem. So what I'll do is I will draw this in a different picture. Actually, all of this happening in the same space. And I'll draw it separately so you get a better understanding about it. So here you have the board. Remember the pulley and the board, there is a gap. Weight and the board, there is a gap. So nothing is touching. Huh? Nothing is touching. So here you go. Here string passing over. Passing over. Weight is here. Weight is here. Weight is here. What you do first is, all of us square, no set square is something like this. In your instrument box, there are two set squares. 45, 90, 45, 30, 60, 90. Check and see if you have instrumentation box, you have two set squares. Some of you all have never used those set squares in your geometric, representation. Some of you all even don't know that angle is 45, 90, 45 in one, 30, 90 and 60 in the other. Actually, you have been using your compass to find 60 and 30 and 45. You can use the set square to quickly find it. Let's say somebody did not know O-level geometry, use a set square to find it. Then using the compass, keep and just put two lines. The examiner won't know. That's how simple the maths works. Is it clear? Anyways, now look, take any of the set squares, no problem. Take any of the set squares. Don't forget, white sheet of paper is behind. White sheet of paper is behind. Right? Using drawing pins, you can fix it on the board. What you do is, I'll show it here. Place the set square perpendicular to the rope. Why am I keeping it like this on top of the rope? So the rope doesn't move sideways. Place the set square perpendicular to the rope. Push it slightly and make a point on the white sheet of paper. Okay. Then move the set square slightly down. Move the set square slightly down. And then mark this point as well. So what are we doing? We are marking 2 points on the white sheet of paper which are parallel to the pink color string. Repeat the same procedure to the other side as well. Repeat the same procedure to the other side as well. Keep a set square here. Make sure the string cannot move sideways. Keep a dot there. Move the square forwards. Here you go. Keep a dot. And where all the string segments meet, keep another dot there. Then what you do is remove the piece of paper. Remove the piece of paper. Here you go. This is your piece of paper. This is your piece of paper. On your piece of paper, you will have dots like this. two dots there. That's the dot there. Then there are two dots here. Think carefully regarding the basic Newton's law knowledge you have. This part is in equilibrium. That means what can you say about the tension here? Tension is equal to 40. This part is in equilibrium. What can you say about the tension there? 50. So this whole line tension is 40. This whole line tension is 50. 40 and 50 will have a resultant force. That resultant force should be equal to how much? 60. Simple. That is why this dot or the center point here is at rest. Understood the common sense connection? This string is at rest. So tension equal for light string, not heavy rope. Tension equal 40. This string is at rest. Tension equal to 50. This string segment 40 means here 40 gram tension. This string segment same string, so 50 gram tension. 40, 50 will give you a resultant. Resultant should be equal to how much? 60. So what we are doing now is just to check whether parallelogram law is correct. We are going to draw a parallelogram. We are going to find the what you call diagonal and show that the diagonal is equal to how much? 60 grams. Understood? Okay. So for the first one, I'm assuming that the what you call holders have no weight, or in other words, this weight is with the holder. This weight is with the holder. Easy, no? This weight is with the holder, with the holder, with the holder. So everything is with the scale pan, the total weight. Easy. Understood? So here the total weight is 40. Otherwise 40, if the weight is only 40, then you have to add the weight of the scale pan as well. If the weight is only 50, you must add the weight of the scale pan as well. I'm just telling, just to make it simple, whole thing is 40. Whole thing is 50. Whole thing here is what? 60. Understood? No? Simple. Right. Now what you're going to do? Right. We have 3 lines, dots there. We will take a suitable scale. So here, whole thing is 40. Whole thing is 50. Whole thing here is what? 60. Look at the board carefully. Yeah? I will take 1 centimeter equals 10 grams. 1 centimeter equal 10 grams. So these are all grams. 10 grams. That means, tell me, this line here represents how many grams? Understand? Quickly tell. String here represents how many grams? 40 grams. 40 grams means what's the length? 4 centimeters. Right. So what you do is, you take your ruler, keep the ruler here, draw joining the 2 points, 4 centimeter length. Now tell me, what can you say about this string segment? What's the weight there? 50 grams. 1 centimeter, 10 grams means what's the length representing the weight? 5 centimeters. So here you have the points. Here you have. I'll join it here. 5 centimeters. Now you must complete the parallelogram. Now you must complete the parallelogram. So I will make it a bit slightly bigger. Just to complete it, otherwise the dots are somewhere down. How do you complete it? There are simple ways of completing. For this, you need just basic geometry. I, of course, will use a compass. How will I use the compass? Look at this. Parallelogram means what? This side 4, this side 4, no? This side 5, this side what? 5. What I'll do is I'll measure 4, put here, put 1 arc length. Then rhombus I'll measure 5. I'll keep it here, another arc length. So now what? Now if I join, yeah, if I join this and if I join that, parallelogram is formed. Right? This is 5 means this is also 5. This is 4 means this is also what? 4. Understood? This is how simple to do it. So here 4, here 5 are where both the arcs meet from here to here 5, from here to here 4. Parallelogram is formed. Understood? Once the parallelogram is formed, next job is use the ruler, join the diagonal. Use the ruler, join the diagonal. First job is check whether the diagonal is vertical. Diagonal is vertical. Next is measure the diagonal. And if you measure length, according to physics, the resultant here should be equal to how much? 60 grams. Length how much? 6 centimeters. Yeah. So you know 1 centimeter is 10 grams. 6 centimeter is how much? 60 grams. What can you say about the principle? Principle of parallelogram of forces is correct. Understood? How can I use this to find the unknown mass? Simple now. We know no? Whatever the diagonal is giving is the resultant. Now imagine there was an unknown weight here like a stone. What I have to do is, if I don't know this even, no problem. I must draw the parallelogram correctly. For this line correctly. Complete the parallelogram. The diagonal will give you what? The unknown weight. Is it clear? The diagonal will give us the unknown weight. Understood? Okay. So 1 centimeter, 10 grams, 6 meter is going to be what? Draw this a bit slightly correct. 60 grams. You know? So this is your principle of parallelogram of forces, trying to find the unknown. What I have done first is, I have used known weights to show the parallelogram law is correct. Once the parallelogram law is correct, then I can what? Find the unknown. Understood? Okay. Let's write this down. Procedure. Procedure. Let's write procedure number 1. As shown in figure number 1, as shown in figure number 1, as shown in figure number 1, we connect the two centers of the pulley such that they are in line with each other. Such that they are in line with each other. Such that they are in line with each other. We then pass a light string over the pulleys. We then pass a light string over the pulleys. We then pass a light string over the pulleys. And hang two weights. And hang two weights. Such that the total weight with the scale pan is 40 gram and 50 gram respectively. Such that the total weight with the scale pan is 40 grams and 50 grams respectively. 40 grams and 50 grams respectively. Neither the string nor the mass will touch the board. Neither the string nor the mass will touch the board. neither the string nor the mass will touch the board as it moves freely. As it moves freely along the board. As it moves freely along the board. As it moves freely along the board. Right. Next point. Keep space to draw figure 1. Keep space to draw figure 1 and this part. Okay? Figure 1 and this one. Next point. So about quarter page keep. Okay? Point number 2. In between the two pulleys, in between the two pulleys, in between the two pulleys, we connect. In between the two pulleys, we connect a known total weight of 60 grams. A known total weight of 60 grams. And this will form a Y-shaped system. And this will form a Y-shaped system as indicated below. To form a Y-shaped system as indicated below. This will form a Y-shaped system as indicated below. Indicated below in figure 2. Sorry. Indicated below in figure 2. Next point, right? Just to check if there is friction in the pulleys. Next point. Just to check if there is friction in the pulleys. Just to check if there is friction in the pulleys. We pull the center weight slightly down and we release it. We pull the center weight slightly down and we release it. We pull the center weight slightly down and we release it. And we keep looking at the Y junction. Don't write Y junction, WHY junction. Y junction. And we keep looking at the Y junction. Yeah, Y junction. Y junction. If it goes back to its initial position, if it goes back to its initial position, if it goes back to its initial position, we say that there is no friction in the pulleys. We say that there is no friction in the pulleys. We say that there is no friction in the pulleys. Comma, if it doesn't go back to its initial position, if it doesn't go back to its initial position, we say that there is friction in the pulleys. We say that there is friction in the pulleys. We say that there is friction in the pulleys. Okay. Keep space to draw. Figure number 2, quarter page. Next point. We place a set square. We place a set square perpendicular to the string segments. We place a set square perpendicular to the string segments such that the string segments cannot move sideways. Such that the string segment cannot move sideways. Such that the string segment cannot move sideways. We move the set square and mark 2 points on the string. We move the set square and mark 2 points on the string. Which will also create 2 points on the sheet of paper behind. Which will also create 2 points on the paper behind. Which will also create 2 points on the paper behind. Okay. Next paragraph, right? We repeat the same procedure for the next string segment. We repeat the same procedure for the next string segment. We repeat the same procedure for the next string segment. So that 2 points are marked on the sheet of paper. So that 2 points are marked on the sheet of paper. So that 2 points are marked on the sheet of paper. 2 points are marked on the sheet of paper. Next point. Where all the string segments meet, the y junction will form. Where all the string segments meet, the y junction will form. Where all the string segments meet, the y junction will form. Here also we create a mark. Here also we create a mark. Here also we create a mark. So that a mark is formed on the sheet of paper. So that a mark is formed on the sheet of paper. So that a mark is formed on the sheet of paper. Okay. Keep space to draw figure number 3, quarter page now. Next point. We now use a suitable scale. We now use a suitable scale. We now use a suitable scale. Example, 1 gram equal 10 grams. You can use anything. Huh? I'm just giving an example. Okay. Always no need to use this. 1 gram equal 10 grams. We use, 1 centimeter equal 10 grams. We use a suitable scale. 1 centimeter equal 10 grams. And we draw a 4 centimeter line on the left hand side. We draw a 4 centimeter line on the left hand side. we draw a 4 centimeter line on the left hand side, which will represent 40 grams, 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 comma. We draw a 5 centimeter line on the right hand side. We draw a 5 centimeter line on the right hand side, which will represent 50 grams, which will represent 50 grams, which will represent 50 grams. And using a compass, we can complete the parallelogram. We can complete the parallelogram. We can complete the parallelogram, comma. Draw the diagonal and check whether it's vertical. Draw the diagonal and check whether it's vertical. Draw the diagonal and check whether it is vertical. And we measure the length of the diagonal. And we measure the length of the diagonal. And we measure the length of the diagonal. We measure the length of the diagonal. The diagonal length will be 6 centimeters. The diagonal length will approximately be 6 centimeters. Most probably. Approximately be 6 centimeters. Which will give us a weight of 60 grams. Which will give us a weight of 60 grams. Which will give us a weight of 60 grams. Which is the total weight connected at the center. Which is the total weight connected at the center. Which is the total weight connected at the center. As shown in figure number 4. As shown in figure number 4. From this we can say the diagonal will give us a force. From this we can say diagonal will give us a force. The diagonal will give us a force which is equal and opposite. Which is equal and opposite. Which is equal and opposite to the weight connected at the center. Which is equal and opposite to the weight connected at the center. Which is equal and opposite to the weight connected at the center. Next line put a star and right. Therefore, if we connect the unknown weight, therefore, if we connect the unknown weight like a stone, therefore, if we connect the unknown weight like a stone, if we connect the unknown weight like a stone to the center, to the center. And if we draw the parallelogram, And if we draw the parallelogram, and if we draw the parallelogram, the weight represented by the diagonal is the unknown weight. The weight represented by the diagonal is the unknown weight. The weight represented by the diagonal is the unknown weight. Okay, no? So there are some more variations in this. But up to now, I think everything is clear. Clear. So whatever you hang here, the unknown weight, whatever weight you hang here, and the weight represented by the diagonal, both are what? Same. Is it clear? Okay. So whatever weight you hang here in the center, and the weight represented by the diagonal, both are what? Same. So if you hang a stone here, diagonal gives you the weight of the stone. Approximately will give. Yeah, if you hang, let's say, a glass top or something, that weight and the diagonal weight both are what? Same. Okay, no? Right. Please draw these diagrams now. Figure 1, figure 2. Figure 1, figure 2. Please draw quickly. Shh. Quickly draw. Shh. Quickly work. Those who have done this practical in school, put your hands up. I'll show you a video as well. Check and see if you did it like that. First, let's draw it like this. Later, I'll show you the video. Earlier one, everyone finished. No? Quick to draw. Figure 3, figure 4. Figure 3, figure 4. Okay. Now, instead of using the set square, some schools will use the plane mirror. How many of you have used plane mirror? We have few of you all who have used the plane mirror. Plane mirror also can be used. Yeah. Have you all finished drawing this? Because I can redraw on top of this. That's all. Anybody finish figure number 3? People who are still drawing figure number 3, put your hands up. One person. Quickly draw. Now what happens is, now here instead of using the set square, you can, because there's a gap here, no? Here, string, board, there is a gap. String and board, there is a gap. What we can do is, look at the board. We can place the mirror underneath the string. We can place the mirror underneath the string. We can place the mirror underneath the string, like this. So mirror is there underneath the string. So if you keep a mirror and a string, what happens? You can see the image of the string. If the image of the string and the string are what? Parallel to each other, on top of each other, or coinciding with each other. In other words, you will see only as a single line. You can't see two lines. Understood? That means if the string and its image are coinciding with each other, okay, if I draw it separately here, look at the board below. Here you have the string. Here you have the string. You put the mirror underneath it. Tell me, how many strings can you see here? One. But how many images are there? Two. You have the string and the image on the mirror, both. String and the image are coinciding with each other. Then what we do is, here and here we place 2 points. There and there we place 2 points. So same way here, you can keep the plane mirror under the string. When the string and the image coincide with each other, what happens? You can get the 2 points. So using the set square also you can get. Using the plane mirror also you can. Okay, no? Put a small star and right there. Instead of using the set square, we can also use the plane mirror. We can also use the plane mirror when we mark points on the string. When we mark the points on the string. When we mark the points on the string. We place the mirror under the string. We place the mirror under the string. We place the mirror under the string until the string and its image coincide with each other. Until the string and its image coincide with each other. Coincide with each other. Until the string and its image coincide with each other. We mark 2 points on the string. Then we mark 2 points on the string as indicated in figure number 5. As indicated in figure number 5. Quickly draw figure number 5. That's an optional situation, but Some schools actually use a plane mirror. Some people use set square. You will use set square to do the practical set square. Nobody, no? Everybody has used the, I mean, whoever did it, used the plane mirror. But in the practical workbook, they are given set square or mirror. So you should know both methods. Both methods. Right, no? Quickly, quickly. Okay, no? So plane mirror is kept under the string until the string and the image coincide with each other. Okay? Right. Shh. The next question is, most of the time, the diagonal will not be vertical. Listen, huh? Why should the diagonal be vertical? The hanging weight here is vertical. So same line means diagonal should be what? Vertical. Equal opposite force. But majority of the times, the diagonal will not be vertical, it will be slanted. When you did the practical, if you got a vertical line, that means what? You have done some magic to make the line what? Straight. When you did the practical in school, if you by any chance got a perfect vertical line, somehow you have done a small magic to make it what? Straight. Because practically, that is impossible. These are the reasons. First one, shh, there might be friction in the pulleys. And the strings you are using might be heavy. If you are using slightly heavy ropes or heavy strings, what happens is, location to location, the tension will change. So here you can say 40 grams here it might be slightly different. Here you might say 50 grams, here it will be slightly what? Different. Third one, now the ones who did the practical, imagine your practical apparatus at school, you know. Most of the strings had knots. In the strings you use, if there are knots, put your hands up. Knots. guaranteed you can't get it vertical. If you got it vertical, that means you slightly what managed to put the mark on somehow to make it vertical. Now, when you're doing the school practical, don't try to get it perfect. The reason why it's called a practical is you can't get it perfect. That is why in your practical sheet, bottom there is something called discussion. Then you must discuss how this changed. Yeah, true. The perfect one is this. I got this. The reason maybe these are the reasons. For that only they give you marks. Huh? Some of you are doing the practical in the lab means I must do it perfectly like the textbook. You call it a practical because what? There is going to be errors. Your job is to what? Identify those errors. Understood? So don't try to do a practical perfect. If you do a practical perfectly, guaranteed that something is wrong somewhere. Either you use some of your personal magic or you didn't do the practical by your own self. Somehow you imagined or got some perfect points and you drew the graph or whatever. Then only what you want anybody, anyway, experienced teachers know whether you have lied or what, whether you got the actual graph. If you get the actual workings, that means most probably there will be slight variation. If the practical is true, if it's what you call too good to be true, guaranteed something is what wrong. Some of you all draw perfect graphs. Y equal mx, it goes exactly to the 0, mark. You might write the equation y equal mx, try to draw the graph y equal mx. Sometimes because when you take practical values, the points might what? Change. Those are called, you call it outliers. You know, those points are there. When you draw the best fit graph, it might slightly be y equal mx. Maybe some other variable is also there. You don't know. So you have to account those as well and do the discussion. The idea of doing the practical is doing the practical almost correct, which is about 90% correct. 10% there will be small variations. That is what you must discuss in the discussion. Yeah. Why isn't it vertical? Friction might be there in the pulleys. Ropes might be heavy. There might be knots or kinks. We call that kinks. Knots or kinks in the rope. Knots or kinks in the rope. Then also tension will what? Change. Yeah. Sometimes you might have drawn the parallelogram taking only the weight of the weight that you hung. You forgot to take the weight of the scale pan. If you forgot to take the weight of the scale pan, only you took the weight that you put. Now here total weight is 60. Total weight is 50. Total weight is 40. That means weight and scale pan both together is 50. Then weight only may be about what? 40. Scale pan, let's say 10. So weight is 40, scale pan 10. Weight is 30, scale pan 10. Weight is 50, scale pan 10. Sometimes you will draw it only for the weights you put. That means 40, 30, how much? 50. Then again, diagonal won't be vertical. Why? Actual weight is different. You are drawing for a different weight. So you must redraw it for the actual total weights. Understood? Sometimes, check and see most of your apparatus in school, they are a bit buckle. Eh? Sometimes the center lines are not in line. None of you all here fix the pulleys, put the rope over. The pulleys are already fixed. People who fix the pulleys and did from the beginning, put your hands up. You yourself fix the pulleys. When you went to your school lab, the pulleys are fixed, the rope was already there. Both the side weights also were there. Center weight was also there. True or false? Put your hands up. Everything was there. Eh? Everything was there. You only had to pull and release. The mirror, put the 2 points. That's all. 5 minutes work. Job done. Center not in line also. Diagonal will not be what? Is it clear? Okay, no? That's right. No, no, shh. Now, this means check and see. When you go to your school lab, when you do it, don't try to get perfect answers. Do the practical. See where it might go wrong. Because your exam question will be based on not the perfect things, the things which might go wrong. Understood? Practical question structured essay, they'll ask you how this practical may go wrong. So you should know those. Understood? That's right. The diagonal most of the times will not be vertical. The diagonal most of the times will not be vertical. This is because point form right. Huh? First one. There is friction in the pulleys. There is friction in the pulleys. There is friction in the pulleys. Roman 2. Strings are heavy. Strings are heavy. From point to point, the tension will change. Strings are heavy. From point to point, the tension will change. Strings are heavy. From point to point, the tension will change. Next one. There might be knots on the string. K-N-O-T-S. Huh? There might be knots on the string. There might be knots on the string. K-N-O-T-S. Knots on the string. This will also cause tension to change. This will also cause tension to change. Next one. We might have drawn the parallelogram without considering the weight of the scale pans. We might have drawn the parallelogram without considering the weight of the scale pans. We might have drawn the parallelogram without considering the weight of the scale pans. Next one. The center of the pulleys are not in line with each other. The center of the pulleys are not in line with each other. Center of the pulleys are not in line with each other. Center of the pulleys are not in line with each other. There is one more important thing. Sometimes when the masses are moving, this mass is knocking on the board. When you all did the experiment, masses were knocking on the board. Put your hands up. You can't get vertical perfect diagrams. Yeah. Sometimes the string is touching on the board. Friction is there. You can't get what? Vertical straight diagrams. Diagonal, sorry. You know? So those are, you can't say, I can't do the practical because it's striking the board. No, you do the practical. Write the discussion. Why isn't it straight? Then the examiner knows, this fellow knows his onions. He knows his work. Is it clear? Understood? You know? Right. Sometimes when the masses are moving, sometimes when the masses are moving, sometimes when the masses are moving, the weight and the rope might touch the drawing board. The weight and the rope might touch the drawing board. This will cause additional friction. This will cause additional friction. Causing the diagonal to not be vertical. Causing the diagonal not to be vertical. Okay, here you go. Right now, drawing board is there. I'm sure all of you all can see this, no? Tassos can see. Here the pulleys are there, centers are in line. Here the white sheet of paper, that's the drawing board. Simpler version. Huh? What we are doing here is, so they have made it simple. They have kept the pulley exactly on top. So if this was flat, center will be in line with each other. The problem comes if you start hanging the weights on the board. Then you don't know where the centers will be. Is it clear? So if you can use this as a reference, easier. So there you go. This was hang it like a mala and kept and kept. He has already made it like a mala, he put it. Finished now. End of story. It's also good. So these are all, you can see the known weights. These the weight holder. There. That's the weight holder. So can you see now? This is still touching the board. Can you see? Can see, no? Right. He settles it. Slightly settle it. Pulleys are in line. There you go, the central location. Huh? Yeah, central location there. Normally what they do is, now, even like this, we don't allow additional strings to hang. Because these additional strings can touch. So what you do, here you go. Plane mirror is kept underneath. I'm sure most of you are doing it like this. Plane mirror is kept underneath. I'll show another one with the set square. String and line, string and mirror in line means, there you go. Draw 2 points where the string and the mirror are in line. So on the sheet of paper, there you go. String and the mirror are in line. 2 points are marked. 2 points are marked. So you're doing it in front, that's why you can't see the whole thing. String and the mirror are in line with each other. Okay, no? There you go. You can see now here. The image and the string are in line. You can see as one. You can see as one. Right. So different configurations. Different weight systems, the basic idea is always the same. Now, whether you tie it in the corner, the knot will go to the corner. There is no problem. Huh? If you tie at the center, the knot will be at the center. That is also no issue. So here you have points. You can see them. Just circle those so you can clearly see it. So this is 40 gram. These also 40 gram. I think both side weights are same. 40 gram, 40 gram. So if you use a scale, if I use 1 centimeter, 10 gram, 4 centimeter here, 4 centimeter there. That was the scale use. Okay. Make sure that the pencil is very thin. You have use a HB pencil with a thinner point. Thicker the point, sometimes you'll get the line wrong. It should be very sharp pencil. Normally for all practicals, you use the HB pencil. Yeah. HB pencil has to be used. Right. There you go. Circular arc is drawn. Shh. Circular arc is drawn using your compass. Drawing this part here is not important, but shh, to get a comparison, it's easier. Drawing this line is not important. We never drew this, no. These two enough. But you can check whether it's vertical or not. Yeah. You can check whether it's vertical or not. Okay. What they are saying is, shh, this weight represents the tension here. This weight represents the tension there. That's our assumption. It might change depending on the weight of the rope. But this weight here, tension here and tension there are same. This weight here, tension here and tension there what? Same. This weight that is hanging in the middle, this tension is same. Okay, no? Fast forward a little bit. Right. This is from one of the teachers at Royal College. Right. Don't talk. Some fellows are, you are not even done this, but you can. Okay, here you go. So what you do is fix the sheet behind. See the procedure. This teacher is the one who makes the Royal College paper. The one that you all search and do and can't do. Okay. So small sheet of paper is good enough. Shh, don't talk, don't talk. So there you go. So he makes sure that and he's using a set square method, I think. Yes, he is. Exactly where the string segments meet. Exactly where the string segments meet, a mark is put. Then I think the mirror method is used, much more easier. Mirror method is used so that coinciding mark is found. Coinciding mark is found. There you go. Then what you do is you pull the center weight down, slightly release it. What we want to check and see whether the point goes exactly to the same point. If it doesn't go to the same point, that means there is what? Friction. Yeah, there is friction. So there you go, the pulleys. So here, Royal College board, they are fixed. I think already fixed center. You can also pull that and see any mass you can pull. Any mass you can pull it down. There is no preference. Huh? Normally, what we use the center mass is easier to look at the Y point. Easier to look at the Y junction. Otherwise, any mass you can what pull and release. Okay. No? So there you go. Set square is kept. We make sure that the string doesn't move. That's the requirement. Huh? String should not move. Then the sheet of paper is taken out. These are your points. That's the vertical line. Shh. Just to check the reference. Here you go. So you draw the straight line, then you use the set square. This should be exactly there. Exactly there. Shh. He is shown just to show the procedure. You all are not here judging anybody. Your judgment is not important. Nobody cares. Okay. You all look and see how it's done. You laughing and making comments about the video is not important for me. Neither is it important for you. Because you're going to write the exam. Yeah. Here's the rule. 1 centimeter, 5 grams. Here 50 gram each. So you need about 10 centimeter that way, 10 centimeter this way. Yeah. Fellows who give judgment. Those are the fellows who fail at the end. If something is shown, you look and learn from it. Don't nobody to judge them, and who are you? You are just passed your O-level exam, trying to pass your A-level exam. Check and see how many questions you ask on the WhatsApp group. Most of you all don't even know. You are out shut and learn. There you go. 10 centimeter mark. Now, I think he'll show two methods. One using the set square. How to use the set square and the ruler to draw a parallel line. See, keeping the ruler by moving the set square, you can draw a parallel line. You keep the set square parallel to this moving. Same way, join the vertical. From the vertical you measure, you keep the zero mark exactly coinciding there. To that particular point, 10 centimeters. So 1 centimeter is 5 grams. So the center one should be 50 grams. Center one will be 50 grams. So you check the center weight there. The center weight here, okay, you hung 50 grams. It is also 50 grams. That means what? So the reasons why it might not be straight also you can see. So this weight here, yeah, it's 50 no. Have you at that bit, you are hanging a stone. There you go. That is your unknown weight. That is your unknown weight. So we are not changing the corner two. So quickly you put your A4 sheet there. You can see clearly there's a nice gap. Because there's a gap only, the sir can nicely stir. There you go. Make sure that the string and the rope are parallel to each other. Once you make all the points, take it out. So 50 grams, 50 grams. Same scale, 1 centimeter, 5 grams, so 10 centimeter there. So now he's using the compass method, which is the easiest. So check the diagonal. 15.4 centimeter. So 1 centimeter, 5 gram, multiply this by 5. So how much? Around 77 grams. So how do you check it? Now the stone is there, no? You can use a triple beam balance to check it. There you go, 77 grams. So what you do is you remove the stone. Triple beam balance. I hope you all remember the triple beam balance. You move the heavier weight first. It went no, so bring it back to 0. Bring it back to 0. These all dot now here. When you move the 10 gram weights, move it to 80, it goes down. Then move it to 7. Then move the 1 grams. We want to make sure that this line, so you can see. So you can add the weights. 70, almost 7. Between 7 and 8, 77. Okay, no? Right, there you go. So that's how that practical is done. This is the next one, which I will show in a while. Right now? Right. Okay. Practical number 6. Practical number 6. Practical number 6. Let's write finding an unknown mass. Finding an unknown mass using principle of moments. Finding an unknown mass using principle of moments. Finding an unknown mass using a principle of moments. So using principle of moments. Right. So what is your theory? Theory means we are going to balance this. Huh? So first we take a ruler with the board. We are balancing the ruler on a knife edge. We are balancing the ruler on a knife edge kept on a wooden stand. Observe. What we do is, here we hang a known weight. Let's say M naught. Here we hang a unknown weight. Let's say M. Known weight, unknown weight. Let's say this distance is X. This distance is what? Y. If the ruler is balanced, what can you say? If the ruler is balanced, you can say clockwise moments equal what? Anti-clockwise movement. Now here, this part here we say M. This part here we can say M naught G is there. Clockwise moments equal anti-clockwise moments. Mg into Y equals M naught G into what? So Gg cancel off. My equals M naught X. Okay, no? M naught X. Now, this is your unknown mass. Unknown mass is M. M naught X divided by Y. But the problem is this. We can't use a single reading to get accurate value. So what we do is we draw a graph. And from the gradient of the graph, we get a much more accurate value. Now you might ask me, sir, is this the most accurate method? No, the accurate method is take this stone and keep it on a scale and measure it. What is that? What is the objective of the practical? Practical is you're using moments to get the mass, and you're checking and seeing how close this mass is to the actual value. That's all. Some of you all think, sir, isn't there an accurate method? No, there are accurate methods. But you're using the principle and you're finding the mass, and you're checking and seeing from this principle how close is the value I got for the actual value. That's the method. That's the practical. It's not perfection always. Huh? Perfection is divine. You can't reach perfection. What you're trying to get is what you're trying to get as close as possible to the actual value. Okay, no? So here, what you're using is principle of moment. So here, yes, you can get the unknown mass, but this is not accurate. So what we do is we draw a graph. That means we take for many points. We change the location of the known mass or unknown mass, and we change the other one also, so it's balanced. We get X and Y. We change the location of the known mass and then change the location of the unknown mass. Like that, for different points, we get what? Different X values, we get different Y values. And then we plot the graph. From the gradient of the graph, we can find the unknown. People who have done this practical in school? Few. Right, good. Now, the principle is this, basic principle. What you're using is you're using a meter ruler. Here, meter ruler is there. Here we have a knife edge. Knife edge. Sometimes you might get a wooden edge. This is a wooden block. This is a wooden block. This is the unknown weight or unknown mass. these are known weights. Known weight. Okay, now let's side with theory. So remember, perfection, don't look for perfection in practicals. If you are looking for perfection in practicals, you'll get fed up. Don't look for perfection in practicals. You're trying to get as close as possible. That's all. Let's write. Let's write. We hang a known weight on one end. Known weight on one end. I use the same symbols the resource book has used. Known weight on one end. And an unknown weight on the other end. And an unknown weight on the other end. Until the ruler is balanced. Until the ruler is balanced. Until the ruler is balanced. We then can measure x and y. We then can measure x and y. And then find the unknown mass. And then find the unknown mass. Then find the unknown mass. Next time put a star and write. Finding it for one measurement will not be accurate. Finding it for one measurement will not be accurate. Finding it for one measurement will not be accurate. So we change the location of the unknown weight we change the location of the unknown weight and to balance the ruler at the center of gravity, and to balance the ruler at the center of gravity, we change the location of the known weight. We change the location of the known weight. And we plot a graph to find the unknown mass. And we plot a graph to find the unknown mass. And we plot a graph to find the unknown mass. Okay, now we don't find a single value. What we do is we'll plot a graph. GG cancel off M over M naught times X. So this graph is of the form what? Y is equal to M. For different values of X, you find different values of Y, plot the graph. From the gradient of the graph, you can find the unknown mass. Simple. Draw this and get this relationship. Y is equal to mx form. Y is equal to mx form. Quickly, yeah? Now, I'll teach you something which is not in this resource book as well. Resource book is actually pretty simple and direct. In reality, there are a few variations which occur. The ones who did the practicals, I will tell you this, check and see whether you found it when you did it. Okay. Now write this down with. So all the apparatus needed also is there. I have marked it. No need to separate it, right? The strings you must write, light strings. Light strings. Okay. So if you're your term exams and all, if they ask, I'll ask you certain questions. They'll ask you from those. So you should know the answers. So M naught is known weight. I'm using the symbols they are given in the what you call resource book. See, you know, M is the unknown weight. M naught known weight. The G will of course cancel off. Distance from the known weight to the center of gravity Y. Distance from the unknown weight to the center of gravity X. Sometimes in your school exam, they can change the source and give. Don't worry. There is no problem. General is change the location of the known weight, find the location of the unknown weight until the ruler is balanced. Okay, no? Okay, right? Proceed here. Proceed here. Proceed here. Let's write point number 1. Place the knife edge on a wooden block. Place the knife edge on a wooden block. Place the knife edge on a wooden block. And place the meter ruler on it such that the ruler is balanced. The ruler is balanced at the center of gravity. Ruler is balanced at the center of gravity. Ruler is balanced at the center of gravity. Right. As shown in figure 1. As shown in figure 1. We take the reading where the knife edge is. We take the reading where the knife edge is. We take the reading where the knife edge is. Now, if the reading here is 50 centimeter, you take 50. If the reading is 49, you take it as 49. Very important. We take the reading where the knife edge is. Second point, next point. That's right. Using a string segment, using a string segment, tie the unknown mass. We tie the unknown mass. We tie the unknown mass. And we hang it. And we hang it. About 5 centimeters away. About 5 centimeters away from the knife edge. About 5 centimeters away from the knife edge. About 5 centimeters away from the knife edge. Next point. We then take a known weight. We then take a known weight. Is important. Huh? Which is approximately equal to the unknown weight. Which is approximately equal to the unknown weight. Which is approximately equal to the unknown. Now you might ask me, sir, how do you know both are approximately equal? Now you take the stone to your hand and then you take a known weight, you will see both are what? Almost the, you will get a feeling. In that point you start. Don't use a scale to start measuring and doing it. Then pointers, no? Is it clear? Take the unknown weight stone, then a known weight to your hand. If they are almost the same, right? There you start the experiment. You know? Right there. Take a known weight, which is approximately equal to the unknown weight. And hang it on the opposite side to the wedge. And hang it on the opposite side of the wedge. Knife edge. Until it is balanced at the same center of gravity. Until it is balanced at the same center of gravity. Until it is balanced at the same center of gravity. And we measure distance y. And we measure distance y from the knife edge. We measure distance y from the knife edge. We measure distance y from the knife edge. Right. Okay. Next point. We change the unknown weight in equal intervals of 5 centimeter from the knife edge. Equal distance of 5 centimeter from the knife edge. Edge 5, then 5 means 10. Understood? No? Look. We change the position of the unknown weight at 5 centimeter intervals. Yeah? 5 centimeter intervals. I will write like that. We change the position of the unknown weight at 5 centimeter intervals. At 5 centimeter intervals. At 5 centimeter intervals. And accordingly, we measure the distance from the center of gravity. And accordingly, we measure the distance to the center of gravity. Accordingly, we measure the distance to the center of gravity from the known weight. From the known weight. and we tabulate it. And we tabulate it. And we tabulate it. So here you go. Look at the board. Here. From here, 5 centimeter. Normally, most of you all might have started from 10 centimeter. People who started from 5 centimeter, put your hands up. People who started from 10 centimeter. 10 centimeter. People who started somewhere beyond 10 centimeter. Right. What happens is when you start from a larger distance, the number of points you take will be what? Less. By meter ruler, no? Meter ruler here 50, here 50, if you tell. If you take more than 10 centimeter, then you maximum you have what? 3 points. Yeah. Some people, they start from, let's say, 10 centimeter or 20 centimeter. Then they change 5 centimeter gaps. Either way, yeah, there is no problem. Make sure at least you get more than 6 points. Yeah, at least you get more than 6 points. Okay. Now what you do is you plot the graph. Okay. Once you plot the graph and you draw the best fit graph, these are the points you will get. Best fit graph. It will pass through the origin. Once it passes through the origin, you know the variation. What's the variation if I write here? Shh, look. Clockwise moments equal anti-clockwise moments. Mx equals m naught y. Simplified. Y is equal to m over m naught x. Now look at this. Gradient of the graph. Gradient of the graph from O-level knowledge. Huh? I'm reminding you all again. On this line, you take x2, y2. Somewhere here, x1, y1. Some of you all don't know how to draw the graph. Some of you all, you know what you all do. You will keep the ruler like antenna, check and see which number of maximum points it goes and you draw. Wrong, huh? You are drawing the best fit graph. Remember, A-level syllabus, you are drawing what? Best fit graph. That means, doesn't mean that all the points you should be on the graph. But maximum number of points should be what? On the graph. Also, the distance you found in the graph should be very what? Minimum. When you go to university, you will learn a method called least square method to draw graphs. Least square method or regression lines. What they are doing is, they are minimizing these distances. Now, if I show this to you separately, these are details most of you all don't know, even if you all did this practical. So learn this. Here you have a graph. Here you have the straight line. And these are the points you found. Some points are here. Can you see? This is perfect. Right? 3 points above, 3 points below. Distance to that point from the line and this point, same, almost same. Here to here, almost same. This is a good best fit line. Yeah. You might say, sir, none of the points I found is on the line. No. Doesn't matter. Some best fit graphs, none of the points you found will be on your graph. Whoever teaches you, whatever point you find should be on the graph, doesn't know what they are talking about. You're drawing something called the best fit line. The best fit line will uniformly distribute the points around the graph. In other words, it makes sure that the line or the value you find on the line and the value you found actually, the gap between them is going to be what? Minimum. I can use some mathematics and show, because you're minimizing the y value. dy over dx should be what? Minimum 0. Mathematics is pointless here, most of you all. So remember, here what we are trying to do is, sometimes when you draw the best fit graph, the actual point you found in the experiment is not on the line. Don't worry. This line will uniformly distribute the points such that the gap between the value you found and the value on the line will be what? Minimum. That is why you call it least squares method when you go to university. There. And you call this a regression line. Some of the points might be on the line, so don't worry. Some points will be on the line. But whatever points which are not on the line should be what? Very close to the line. Understood? Now, if you draw a regression line like this, these are things you all don't know. Look very carefully. Don't laugh and wait. Look. Now you draw a line like this. One of your points is here, other point is there, other point is here, point is there. Is this a best fit line? Is this a best fit line? Yeah, it is a best fit line. These two are too far away. We can ignore them. They are called what? Outliers. What do you call them? What liars? Outliers. That means you have made a mistake when you took the measurement. Maybe it was reading somewhere closer, you didn't see, you wrote something else. Maybe you were taking wrong measurements, you wrote lies. Yeah. Maybe you didn't do the practical. You are collecting few data sheets from your friends and trying to what? Mark and make. This will happen. I'm telling things that you will do in the future. But here this line is very close, this line is very close, this is on the line. You have only a few points, so therefore what? Most probably this is your best fit. If you draw this somewhere else, will it be best fit? See the distance? Understood? Did you get the point? So you're drawing it so that the points that you found are what? Very close to the line that you draw. Some are far away, those are outliers, you can ignore. Imagine this, you have a graph like this. Here, uniform. One fellow is here. Yeah. Actually, when you are doing the experiment, you must also explain why that occurs. Yeah. Yeah, yes, you have outliers, but why do we have it here? Let's say you're doing the experiment, let's say you're doing this experiment, sometimes you always have to keep the ruler at the center of gravity. Maybe you forgot to keep it at the same location, maybe you got a different point. Every time you repeat the experiment, the knife edge should be at the center of gravity. Because if you move it, the weight of the ruler also comes. Understood? So these are outliers. Don't worry much. Make sure that the remaining points are uniformly distributed. Okay, right. I think now you have a small idea there. How do you select these points? Look. When you select these points, look at the board. Here you go. You are drawing this on a graph sheet. No? Okay, no? You're drawing it on a graph sheet. I just quickly draw it like this. Right. You must select this point. You must select this point such that where the grid line meets, where the edge of the grid line, the graph goes. Here also should be far away, where the grid line exactly what? Meets. Don't ever take points which are like this. Grid line is here, graph is going this way. Can you take these 2 points? You don't know, man. You only know this value. Slightly away, you don't know. Grid line means here. Grid line means the next box comes here. Can you take that point there? No, you can't. Don't take these points. Don't take those points. Can you take this one? Technically, no. It is not going slightly to the right. Here. Can you take this point here? Can you take this point? No. It's cutting somewhere in middle of the box. Don't take. You don't know the value. No, sir, it's very close to this value. I can take. Don't take. Wrong. So this is also very close. No, they will ignore these. These are very small, minute, small errors only are what? Big errors. But here it comes to graphs. Do not take points which are cutting midline. Always when you take the points, it should be exactly where the grid line meets. Now tell me with your O-level knowledge, gradient, if I know x1, y1, x2, y2, gradient, y2 minus y1 divided by x2 minus x2. So gradient of the graph, that is equal to m over m naught. M over m naught is your gradient. So from this we can find the unknown mass. Unknown mass is m. M naught times gradient. M naught times gradient. Okay, no? If you cross multiply here, you can find the unknown. Okay, no? But more than this practical, there are some important things. When you're drawing the graph, make sure you're always drawing what? The best fit graph. Best fit graph. Uniformly distributes. Sometimes you might get outliers. Don't worry, ignore the outliers. Make sure that the line that you draw and the points that you found are very close to that line. Majority of the points should be very close to that line. Some can be on the line as well. But all can't be far away from the line. In what? Not your best fit graph. Remember, the main idea of best fit graph is the graph line you draw and the point that you found is very close to what? The line. Very close to the line. Once you do that, from the take 2 points which cuts the grid line far away. Don't take these 2 points close also. Points that you select, now you will say, sir, it's going to 0, 0, no. Can I take 0, 0? My advice to you, don't. Yeah. My advice, don't. It's easier. Don't select another point. Reason being that take a point where a point that you found is very close to the line. So that means you're getting it closer now. 0, 0 means you don't take a 0, 0. You don't keep this here and that also there, no. So 0, 0 is not a point where you place. So my advice is take a point which is on the line and also far away. Find the gradient. From the gradient, you can find the unknown. Okay, no? Let's write. That is up. Proceed here. And we tabulate. Right. Okay. Next line, right? Next point, right? We then plot the best fit graph. We then plot the best fit graph. We then plot the best fit graph. And we find the gradient of the graph. And we find the gradient of the graph. So you remember. And we find the gradient of the graph. From the gradient, we can find the unknown mass. From the gradient, we can find the unknown mass. From the gradient, we can find the unknown mass. From the gradient, we can find the unknown mass. I'll quickly draw this in. These already drawn, no? Already drawn, no? So this no need. drawn. Put the table. Draw the best fit graph. Table I have put here. Draw the best fit graph. Easiest is like this. Different x values to different y values. So you can put like this. I have written in the note, no 5 centimeter intervals. Different x values to different y values. Plot the graph. From the gradient of the graph, you can get your answer. Draw these two. So you might confuse with x1, x2. I'll make this xa. Easier. xa, ya, xb, yb. Here, yb minus ya, xb minus xa. Okay, no? Remember exam day when they give the graph to draw, the examiners have a, what you call, transparent sheet where the graph is drawn. They will take that transparent sheet and keep on top of your paper. If their line and your line are not in the same line, no marks. Simple. That's how it is done. Nah? Some of you all don't know this. Some of you all think any graph you draw, they'll give marks. No, no. They have a transparent sheet. Have you all seen your bio teachers sometimes? On the transparent sheet, they'll quickly draw and keep it. Like that, there's a transparent sheet that they'll keep on top of your paper. The original line that is supposed to be there in the marking scheme, and your line, if it's going like this, finish. If it's almost close, then they'll give you marks. Because there is a small, corrected variation there, so they'll give you marks. But if it's far away, of course, then wrong. They won't give marks. That is how they correct the graphs. These things you all should know little by little at least. How the examiners actually do it. Some of you all think every single paper the examiner is going to draw the graph and check. Are you mad? They have a transparency. They keep on top and check. That's it. So the math students especially, because you'll be learning straight line in your coordinate geometry. I don't know how many of you have started learning straight line. Anybody who has started learning straight line? Anybody who has started straight line? Learning straight line. You all just check and see least squares method. Least squares method. Least, L-E-A-S-T, squares, S-Q-A-R-E-S, squared method. M-E-T-H-O-R. Least squared method, that is the method they are used, world standard, to draw graphs. Okay. So this is important for you all because you're learning straight line. Okay, no? Shh. Tell me, whatever point you found on the practical, is it a must to be on the graph? Yes or no? No. Where should the points be? Far away from the graph or very close to the graph? Very close to the graph. What do you mean by best fit graph? The graph that uniformly distributes all the points. When you're finding the gradient, you must select 2 points far away. Where? Outside the graph or on the graph? Outside the graph or on the graph for gradient? On the graph. Where the grid line meets. Where? Then y2 minus y1 divided by x2 minus. Okay, no? So right, you can write and finish here. From the gradient, you can find the unknown mass. Right. These are some questions for the ones who have already done the practical. Why aren't we placing the masses? Why do we need to hang the mass? Why can't we place the mass on the ruler? Others also can answer. But these are questions your school teacher or your lab assistant should have asked you when you did the practical. Why can't you place the mass on the ruler? Why do you have to hang it? Think and tell. Don't always start with accurate. I am asking why. Why means there is only one answer. Can't take the exact measurement. Very good. Why? If you place from here to where is the center of gravity? You don't know. But if you hang it, you know whatever object you hang, the string and the center of gravity are in line. So if I measure from the wedge to the string, same distance from there to there, to the center of gravity. If I place it, I don't know where the center of gravity is. Remember, in the exam structured essay, they want direct answers like that. Do not write the A-level structured essay paper like English literature. English literature, whatever you wrote in the first paragraph is also there in the second paragraph. Whatever you explain in the second paragraph is also back again there in the fourth paragraph. Clear? Here you can't write like that. Whatever they ask to the point, write and finish. Why can't I place the object on the ruler and measure? Because we do not know where the center of gravity of the object is to take the measurement. Therefore, we always hang it. Why are you hanging it? Because when you hang, line of action of the rope and the weight both are what? Same. Distance from the center of gravity to the rope, distance to the center of gravity both are what? Same. You know, put star like this. We should never place the object on the ruler. We should never place the object on the ruler. We should never place the object on the ruler because we do not know the location of the center of gravity of the object. We do not know the location of the center of gravity of the object. If we place it on the ruler, but if we hang it, the line of action of the tension of the rope, the line of action of the tension of the rope, the line of action of the tension of the rope and the weight will be the same. Line of action of the tension of the rope and the weight will be the same. And the weight will be the same. So distance from the center of gravity to the rope, distance from the center of gravity of the ruler to the rope, distance from the center of gravity of the ruler to the rope will give us the correct measurement. Will give us the correct measurement. Distance from the center of gravity of the ruler to the rope will give us the correct measurement. So remember this, it's a very important point that they will normally question. Yeah, normally question, right? quickly to show this and finish it off. Right, have a look. Shh. Have a look. Not easy, huh? This practically is not easy to do because you calibrate, you get fed up. This will keep on moving. So this is your knife edge stand. Your patiently is doing it. If you were there, you'll throw the apparatus and go home. He's the one who makes the royal paper. So I'll send this report because these are your, what you call, resource book. There you go. Shh. Right. Now, whatever point it's, now this point is important. Huh? This point should be noted. Because every time you keep the measurements, that you should keep the knife edge at the same point. Why are you keeping at the same point? I think the camera went to the roof. So don't worry much. Yeah, the fan has nothing to do with this practical. Fan has nothing to do with the practical, right? Okay, back again. Shh. Look, 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 look. Look how they make this, huh? The ones who did this practical, did you all do it like this? Answer is no. That's I'm telling you all. Watch these things. Huh? These are, see, time taken to know. You all won't do this. You will do something and go. Yeah. This is like a malmala. You have to put, you see, 100-gram weight. 100-gram weight. That's a 50-gram weight. That's the stone. There you go. Tell me, why are you having this block? Why can't you keep on the table and do? That is common sense. Huh? Some people are sitting on that and waiting. If you don't keep it on the wooden block, you can't hang it. You know? Don't keep like this all. So if you keep like that, the stone is telling why not to keep it. There you go. So the earlier location you remember, now you know quickly where to keep. Here. .50-gram weight is taken. Stone is also almost 50 grams means similar. Why similar? Then M and M not same, almost in the center of the graph, you'll get the line. That is, I will write that also, that I think it is right. So here you go. How much? I don't think 50, but slightly, maybe 50.5, I don't know. Can't see, maybe my eyesight is wrong. Oh, it's blurred. It's blurred. For yours, it's blurred. Ah, now right. 50.5. So don't always think ruler always at the center 50. Yeah? Perfect example. With time, most of the wooden rulers, they warp. Check in the some rulers, they're like this bakal. Why? When the water vaporizes, the wood will what? Turn. Yeah. some check and see some doors now these days cold with weather, no, you can't close the wooden door. The door is open. Bathroom door you can't close because you know why? It's stuck. Yeah, you must put a no enter sign when you go inside. Can you see the way they put it? Now balance. So now you have to measure from here to here and here to here. There you go. It's not easy, okay? 27.1 centimeter from one side. From 50 you have to subtract. 50.5 you have to subtract. 50.5, 27.1 subtract. Then you get the distance. Here, whatever subtract, you get the distance. Okay, no? I think he's move forward. Right? I'll give you his link. You can watch it. You go home. His name is Kosala Pradeep. Shh. Look below. There you go. Now something. Shh. Why did he start the experiment from the corner? You hang the stone on the corner and you check the weight, the distance is known. Because if you hang the stone in the corner and if you can't find the balancing location, then you must what? Change the weight. Understood? Earlier he started the experiment from this corner. No? Why? Then the known weight, there is a shorter distance. Then he knows. If I'm digging this closer, this distance also will get what? Close. But if I put the unknown weight in the corner and this has no distance, then what? I can't do the experiment. Yeah. So first check was done there. Once you did the experiment, did you all do this check? Most probably not. Hang the unknown weight in the corner, hang the known weight somewhere, check and see the balancing point. For the maximum distance, if you can find a balancing point, there's a gap. That means what? You can do the experiment with the unknown weight and the known weight. Then you go 5 or 10 centimeter gaps and then you do the experiment. Sometimes they ask you that in the question. In the beginning of the experiment, why are we placing the unknown weight at the longest distance, right? But to find whether we can find known weight distance. If the known weight is beyond the length of the ruler, then what? We have to find another unknown. We have to find another heavier known weight. Is it clear? Heavier known weight. So if the once that check is done, then you repeat the experiment and you go. So now you change it in 10 centimeter intervals. There also hold it carefully. Move it. Let go. Check whether it's at the same location. Let go. Remember when you're doing the experiment, the fan should be off. That's maybe the reason why he showed the fan on top. If the fan is working, this will keep on what? Tilting. Don't do the experiment near your lab window. Blowing will come. This will keep on what? Oscillating. Understood? So now he is in fast forward motion. There you go. These are only real teachers. You can see whether your school teacher is doing all this and showing you. These are the silent heroes. I thought I should give him a place in my class. You know, changing distances. See the way they have put it, it's easy to move. Understood? Right? Okay. So back again to the equation to find. Okay. Just write this so we can finish it off. Some important points we found earlier. Write this. Shh. That's right. That's right. We select a mass which is almost equal to the unknown mass. We select the weight which is almost equal to the unknown weight. We select the weight which is almost equal to the unknown weight. Because there will be a uniform distribution. There will be a uniform distribution of points around the center of the graph. Uniform distribution of points around the center of the graph. Uniform distribution of points around the center of the graph. You can draw this. Okay? Uniform distribution of points around the center of the graph. So like 45 degrees, huh? Almost, not same, but almost. Now these points are not there in your resource book. Huh? That's why I told you I'll be telling you some important things are not there in the resource book. That's why I specifically used the video done by the Royal College team. Because those are where the points. Full thing is nicely shown. Things which you all don't know. That is why you all say, no, that paper is difficult. This is Mara paper. Mara paper because what? Everything is taught and you don't know. If you don't be a Mara paper, understood? Right? Shh. Next point. The unknown mass is placed at the corner. The unknown mass is placed at the corner. And we check and see if there is a balancing length for the known weight. And we check and see if there is a balancing length for the known weight. We check and see if there is a balancing weight to the known weight. We check and see if there is a balancing length for the known weight. Look at the board now. If this is very close to the knife edge, is it a good thing or a bad thing? I'll ask you this question. If this is very close to the knife edge, is it a good thing or a bad thing? Bad thing. That means when this is coming closer, this fellow is some more close. You can't measure. Clear? Next. And that fellow is in the corner. This fellow, you can't even hang. Good thing or bad thing? Obviously bad thing. That means why is it very close here? First case, why is it very close? Weight is heavy. What should you do? Reduce the weight. Clear? Understood? Once you did the practical in school. If this is very close, you can't take measurements. Then what should you do? Reduce this weight. Then you get what? If this is beyond, that means weight is what? Less. Increase the weight. Yeah. Then only you can get a proper scale to do the required measurements. Understood? Right? That's right. If the known weight is very close to the knife edge, if the known weight is very close to the knife edge, that means we must reduce the known weight. That means we must reduce the known weight. Otherwise, we cannot take accurate measurements. 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 Okay. Right now, now. Okay, then have a break and come. Both practicals done and finished completely. Yeah? Which ones I discussed? Quickly mark the ones you did. I did not discuss the pen now. Just put a tick mark. Discuss करो ना देव again. These are discussed. Okay. Right. Shh. Before we move on with rotational motion, there are a few questions I could not discuss. Page 11, question number 9. Shh. Page 11, question number 9. Right. A sphere attached to a thread is whirled in a circle. When you observe, what are the forces? Shh. will be the mg and tension. Shh. Right. Is number 2. Answer number 2. Ninth one have we done? Up to 12 we have done now. Question number 13. Shh. Page 12, huh? Page 12. This you all know. Shh. Listen. Mg here. Length is L. Angle theta. Shh. Listen. Going in a circular path. What are they asking you? Velocity. I won't develop the full theory. I have taught you. Tan theta is equal to V squared over Rg. Theory. Check and see your note. Shh. Check and see your note. Tan theta equal V squared over Rg. Conical pendulum. Conical pendulum, tan theta equals V squared over Rg. Right? You got? Conical pendulum, second or third example. Got? There you go. Ah, right? No? If you write in terms of omega, omega squared R over G. If you substitute in terms of V, V squared divided by R, G. Now, what is this radius? If you look at this, sin theta is equal to opposite over hypotenuse. Cross multiply, R is L sin theta. So if I substitute here, V squared is RG, R is L sin theta, G tan theta. V squared LG tan theta sin theta. Square root LG tan theta sin theta. This is there in answer number 1. This is there in answer number 1. You know, question number 13, answer number 1. If you're MCQ directly, you should be able to write this. They're asking velocity, no? Right. Quickly write the ones who need it. Question number 14. Shh. Earth rotates with different angular velocity. For an object placed on the Earth's equator, the velocity that should possess by the point to make apparent weight 0. What do you mean by apparent weight? When you are inside a lift, I told you, the normal reaction acting on you is called what? Apparent weight. Now, if you take the Earth, I'll erase the first one. I'll erase one. Here you go. If you take the Earth, this is the equator. If there is a mass on the equator, here you go. Weight is acting to the center. Here you have normal reaction. Normal reaction is your apparent weight. They are telling you apparent weight to be 0 means R is equal to what? 0. For that, what is your omega? What is your omega? Okay. So if you apply centripetal force equal mass into centripetal towards the center, mg minus normal reaction, m, they want velocity, no? V squared divided by radius. Radius I'll put simple R, otherwise confused. Simple R. Now apparent weight is 0 means normal reaction is 0. Cancel off, cross multiply. V squared equal RG. R is radius of the earth. R is radius of the earth. What's the radius of the earth? 6.4 10 to the power 6 into 10 square root. That is 64 10 to the power 6 square root. 64 square root is 8 10 to the power 3. What's your answer? 8,000 meters per second. 8,000 meters per second. Your correct answer is answer number 3. Correct answer is answer number 3. Okay, no? Write there small sentence. Apparent weight means normal reaction will be 0. Apparent weight means normal reaction will be 0. Apparent weight means normal reaction will be 0. Right, no? Question number 15. Read. A car of mass m takes a circular bend of radius r in a horizontal road with speed v. The car will skid. And see or note. On the verge of slipping, maximum possible velocity we found. What's the Vmax? Vmax is mu rg square root. Can you remember? Tell me, for the vehicle to skid, should the velocity be greater than this value or less than this value? Greater than this value. So V should be greater than mu rg square root. Vehicle will skid. Vehicle will skid. Correct answer is answer number 1. Correct answer is answer number 1. 70. 80, 90. Did? We haven't. No, 16 have we discussed. That's I'm asking. Okay, no? Question number 16. Question number 16. Athlete runs a 10-kilometer race with constant speed V1 in a circular track of radius 50. It has been observed that the athlete with velocity V1 completes 10 rounds. 10 rounds, while the other athlete completes 9 rounds. So time taken is the same. Distance divided by speed. 2 pi r is the radius. 10 rounds, velocity V1. Same time, the other athlete, 2 pi r, 9 rounds, velocity V2. 1 and 2 are equal. 2 pi r, 2 pi r, 9 over V2. 2 pi r cancel off. V1 over V2, 10 over 9. 10 over 9. Answer is answer number 1. Right. Shh. So I have taught you all about pseudo forces. Now read the next one. One end of each of the two identical set springs are fixed to two ends of a closed tube. Look below. There is a closed tube here. Here there is a spring. Mass spring. This end P, this end Q, this is mass M. Look at the questions now. Which of the following motions of the system results in the displacement of mass m towards p. That means m is coming back. Right. So imagine you are inside this system. A. Uniform acceleration of the tube in the direction PQ. Tell me, if the vehicle or the object accelerates that way, will the mass come backwards? Yes or no? Yes. When you are inside a vehicle, when the vehicle accelerates forward, you will accelerate where? Backwards. So statement A is not correct. Statement B. Rotation of the tube around the vertical axis passing through Q. Now here there is axis. You're rotating it this way. Imagine you're inside a bus and the bus is taking a bend. Are you going to move towards the center or away from the center? Away from the center. What do you call that force? Centrifugal force. Centrifugal force is what? A pseudo force. So when I'm taking the bend around Q, M will go towards P. That's also what? Correct. Right there. Centrifugal force will act on M. Centrifugal force will act on M. Right. Okay. Question or part C. Vertical motion of the tube under gravity, Q below P. This is a nice question. Most of the fellows will say yes for this without looking at the problem. Q below, P up. Spring is connected. Mass is here. Spring is connected. What are the forces already there? What are the forces already there? Mg is there. Spring forces might be there, no? T1, T2 are there. Now tell me, when this is falling under gravity, there will be a pseudo force which direction? When this is falling under gravity, there will be a pseudo force where? Down or up? Upwards. Mass is there, acceleration is g, so you have mg upwards. mg will cancel off. Now you just have what? The spring. So will this mass go towards P? No. Some of you all will say, sir, there's a pseudo force upward. Yes. Pseudo force is how much? Mg. Mg and mg will what? Can't go. Only A and correct answer number. Yeah. So wait, you might make this mistake. You might think pseudo force upward, it might go towards P. Can't go. Mg is here. That mg, this mg will what? Cancel? Oh, can't go. Yeah. It's like there is no weight. So it's at the same place. Yeah. Right there. When falling vertically downwards under gravity, there will be a pseudo force acting upwards. There will be a pseudo force acting upwards equal to mg. There will be a pseudo force acting upwards equal to mg. There will be a pseudo force acting upwards equal to mg. This will cancel off the weight, so m will not move towards P. This will cancel off the weight, so m will not move towards P. M will not move towards P. M will not move towards P. Okay, no? So A and B correct. Right, question number 18. Question number 18. A light spiral spring has an unstretched length L. Unstretched length L. So here, once it's going in a circle, it's going to be stretched. Radius R. Think carefully and tell me now. Whenever there is a spring, there is going to be Hooke's law. What is your extension? Extension is going to be radius minus L. Here you have force F. What are they asking you? Angular velocity omega. What is it? So centripetal force equal mass into centripetal acceleration acting towards the center. Who is providing the centripetal force? K times R minus L, Hooke's law. Mass into centripetal acceleration omega squared R. Omega squared is K over M, R minus L over R, whole thing square root. This answer is there only in answer number 1. This answer is there only in answer number 1. Right there. Since the spring will extend, since the spring will extend, Hooke's law will provide the elastic force. Hooke's law will provide the elastic force. And this elastic force will act towards the center. And this elastic force will act towards the center. And this elastic force will act towards the center. Once you need it, quickly write it down. Right. Shh. 19-1. Easy. Circular, here velocity V. Shh. Here velocity V. Now what are they asking you? Change in velocity. Can you remember? Delta V is 2V sine delta theta divided by 2. There. From your note. Motion, first page. Not review the circular motion. Change in velocity is 2V sine delta theta divided by 2. Turn and see. See, will you change in velocity vector diagram? Understood? So what is your change? 2V sine, what's the angle here? 90. 90 over 2 means sine 45. Sine 45 means delta V. 2V 1 over root 2. Answer is root 2V. Now where is your change in velocity acting? Change in velocity is acting towards the center. Towards the center, angle 45. Root 2V. So root 2V towards the center, angle 45. What's your answer? Answer number 4. Don't go and draw vector diagram. No need. Directly from the equation, get it. Right. Okay, no? Again, theory, Theory. Okay. 7th question also I have to discuss it. 7th question. Page 10. Question number 7. Good question. Page 10. Question number 7. Read, will you? A toy car connected to a fixed point by an elastic string is shown in the figure. travels in a circular of radius 2r. Initial unstretched length is r. Shh. Anybody still writing this? No one, no? Ah. Shh. Unstretched length is r. Now 2r, r is here. So going in a circular path means here there is an elastic force. Listen. Extension is 2r minus r, which is r. Elastic force is k times extension r. They are telling you periodic time is t. I write in omega. T is equal to 2 pi over omega. Okay, no? Omega is equal to 2 pi divided by t. So let me write the equation here. Omega 1. Centripetal force equal mass into centripetal towards the center. Towards the center. Who is providing centripetal force? Elastic force. Mass into centripetal acceleration omega 1 squared over 2r. Radius is 2r. What is your elastic force? Elastic force is equal to k times r. Mass omega 1 squared. Be careful. What is omega 1? Omega 1 is 2 pi divided by t whole thing squared. Radius 2r. I'll name this equation number 1. Then they are telling you, car is speeding up. Car is speeding up. Now the radius is going to be 3r. Now the radius is going to be 3r. So there's a different elastic force. What is your extension? Unstretched length is r. Now 3r. What's the extension? 2r. Now you can say extension is equal to 3r minus r. How much? 2r. Elastic force Hooke's law. F2 is equal to k times extension. Extension is 2r. This is going in a circular path. They are asking the periodic time, if I'm not mistaken. Yes, periodic time. So let's say the periodic time is T2. T2 is 2 pi over omega 2. Omega 2 is equal to 2 pi divided by T2. Now apply equations. Centripetal force equal mass into centripetal towards the center O. Who is providing centripetal? Elastic force. Time 2 squared, radius is 3r. Be careful. What is F2? K times 2r. What is omega 2? 2 pi over T2, whole thing squared 3r. There you go, equation number 2. Now technically your problem is solved. Divide the first equation by the second equation. Left hand side separately, kr divided by 2kr. M times 2 pi over t whole thing squared radius over 2r. Over m times 2 pi over t2 whole thing squared 3r. Common terms cancel off. Common terms cancel off. Kr cancel off. M cancel off. R cancel off. 2 pi squared cancel off. 2 pi squared cancel off. Here you will have half. This goes to the top. T2 divided by t whole thing squared. Here you have 2. Here you have 3. What will you get? Now if I finish it somewhere here. Cross multiply 3 over 4. T2 divided by t squared. 3 over 4. please take the square root. If you take the square root, root 3 over 2. T2 is equal to root 3 over 2 into T. Root 3 over 2 into T means correct answer is answer number 4. People who got answer 4? Good. So here on the rule. Elastic force will give the required centripetal force. Right there. The elastic force will provide the required centripetal force. That's all. Finished. The elastic force will provide the required centripetal force. Done. Elastic force will provide the required centripetal force. First situation, extension is radius r. First situation, extension is radius r. Extension is radius r. Second situation, extension is 2r. Second situation, extension is 2r. Right, no? Once you need it, quickly write down. Shh. Right. Shh. Anybody still writing this? Quickly write. So what I'll do today for the remaining time is a few special notes. These special notes will be important when we solve equations or problems next week. Yeah. So next week we have a short theory of rotational motion equation, and then we have what? Just to solve problems. Okay. Have you finished, right? Now, last week you learned about moment of inertia. Different shapes have different moment of inertia. Sometimes there are equations for you to remember. I said don't remember. Exam day they will give you the equations. But for your term test, please remember and go because they might not give. Remember, there is something else called radius gyration. If they give you the radius of gyration, directly you can find the moment of inertia. Directly you can find the moment of inertia. Right? Right? Special note. Radius of gyration. Radius of gyration K. Radius of gyration K. Right? Look. If the radius of gyration is given with the mass, mk squared will give us the moment of inertia. Whatever the shape, if you know the radius of gyration, mk squared will give you moment of inertia. That's right. Let the mass of the object be m. Let the mass of the object be m. And the radius of gyration be k. And the radius of gyration be capital K. And the radius of gyration be capital K. We can directly find the moment of inertia as indicated below. We can directly find the moment of inertia as indicated below. As indicated below, right? K is radius of gyration. Mk squared will give you moment of inertia. There. Mk squared will give you moment of inertia. Write down. Right. Next one. Now check and see in your car dashboard. There is something called a RPM meter. Good. 0. RPM meter. What does RPM stand for? Revs per minute. Revolutions per minute. In other words, rotations per minute. How many rotations are taking place every minute? Also remember, revolutions per minute, you have to convert to revolutions per second. Number of rotations per second is called what? Frequency. What is frequency? Number of rotations per second. Look at this board carefully. Yeah? RPM is given capital N. Convert this to RPS, revolutions per second. How do you convert revolutions per minute to revolutions per second? Divide by how much? 60. In 1 minute you have revolutions per second. In other words, is what? Frequency. Don't forget now. I'll write again. T is equal to 2 pi over omega. Can remember no? Huh? We used earlier as well. Shh. Look. Omega equals 2 pi into 1 over T. What is 1 over T? O-level science. 1 over periodic time is what? Huh? Frequency. Omega equals 2 pi. 1 over T is frequency. What is your frequency? N over 60. What is N? RPM. Omega equals 2 pi N over 60. So if they give you revolutions per minute, quickly you can convert to omega using this equation. So you can directly use this equation to convert it to what? Omega. If it's revolutions per second, then omega equals 2 pi. Quickly you can get your answer. So now the thing is, there are some things that you should quickly convert. Without the conversion, you can't move forward. If they give you revolutions per minute, quickly you can convert to what? Omega. 2 pi N over 60. How this N over 60 came? N divided by 60 is what? Revolutions per second. Revolutions per second is what? Frequency. Frequency we can substitute here to get the answer. Clear? That's right. In rotation motion problems, the angular velocity is given in revolutions per minute. Revolutions per minute. Revolutions per minute. Inside brackets RPM. We can convert this into angular velocity omega. We can convert this to angular velocity omega using the following steps. Using the following steps. Using the following steps. Do it, look at me. RPM is given, divide by 60 RPS. RPM directly substitute there. Because RPS is frequency. This is revolutions per minute. Revolutions per minute. This one, revolutions per second. Revolutions per second. RPM, RPS. Okay. Shh. Right. Two more simple ones. RPM is given, don't be afraid, omega equal n over 60. N is in RPM. N is in RPM. Okay? Right. Shh. Look at this. Things that you know. S equal R theta. You all know, no? Divide both sides by time. S over T, theta over T. Tell me, what is S over T? V. What is theta over T? Omega. Shh. Listen. Now divide this by time. V over T, R omega over T. What is V over T? Acceleration. What is omega over T? Angular acceleration. So this is tangential velocity, radius into omega. You remember? V equal R omega with so what? Tangential velocity. This is called tangential velocity. Tangential velocity. So if I write here, this will become what? Tangential what? Acceleration. Omega over T is called what? Alpha. Alpha is called angular acceleration. Shh, listen. Angular acceleration. So A equals R. Please look at the units. Look at the board, look at the board. Alpha is equal to omega over T. Radians per second, we know, no? Divide by second. This becomes what? Radians per second square. Here. Radians per second square. So A is equal to R alpha. Directly you can use. Write down. Write down S equal R theta, divide both sides by time. B equal R omega, tangential velocity. Then divide both sides by time. A equal R alpha. A equal R alpha. Simple ones. Huh? There's one more and then that's it for today. So please look at the practicals. Huh? Some of you all might be having exams next week. The practicals you did, I think you'll remember it. Tomorrow, you will get at least both or one of them you'll get. Maybe a first term, no? You will get an instrument and maybe one of these. Or if they want to make the exam miserable for you, no instrument, only these two. Right? Shh. So how many of you all are in the WhatsApp group? Problem solving? Good. So make sure you can see how active it is. Huh? Always people ask a question, no anammanang cases. Yeah. No advertising, nothing. Purely what? Work. Make sure you all work as well. Huh? Don't just look and wait. Some people don't even know the questions which are put there. Some fellows are watching and waiting. Oh, is this in our syllabus? Those will come to me. Those are the fellows who are not even studying. There. One fellow was asking the question whether the equation b squared equal u squared plus 2as can be applied vertically. And no, can't. Can you apply v squared equal u squared plus 2as vertically? Yes or no? I mean projectile motion we applied, vertical motion under gravity we applied. Now exam is near, no? Now only he is turning the books and checking. So they don't know whether to use which equation where. Yeah. Also, I made another chem group. No? That is also very actively going. I don't know chemistry, but there are people look after. Right. Shh. From this, the final one. Newton's law of rotation. Newton's law of rotation. Shh. Last week, the final note you learned is angular momentum. These what Newton's law of rotation tells you. External torque directly proportional to rate of change of angular momentum. External torque is what? Moment of force. External torque directly proportional to rate of change of angular momentum. Look at the board now. Shh. Torque equals K times delta L over delta T. Experimentally, they have found out K is equal to how much? 1. Experiment. So torque is equal to delta L over delta T. Look at the board now. Huh? But delta L, change in angular momentum. Change means what? Final minus initial. Torque is equal to final angular momentum divided by time. Final means what? I omega minus initial I omega naught. We say initial omega naught divided by T. I'll take I out. Omega minus omega naught divided by T. What is this? Delta T. I'm sorry. Delta T. What is this? Change in omega divided by time. What is change in omega divided by time? Alpha. From here you have a nice equation. Torque is equal to I alpha. Just like F equal ma for linear motion questions. For rotational motion, what are you going to? Torque equals I alpha. Okay, no? So you all know the symbol, no? This is called torque. This is moment of inertia. Moment of inertia. This is angular acceleration. Angular acceleration. This is change in angular momentum. Angular. That's right. Newton's law of rotation states that. Newton's law of rotation states that the rate of change of angular momentum, the rate of change of angular momentum, the rate of change of angular momentum is directly proportional to the torque. Proportional to the torque. Directly proportional to the torque. That's all. Right now. So this is the symbol tau or torque. The other way. Torque, you all know torque, moment of a force. I have taught this in equilibrium as well. Right? Torque directly proportional to delta L over delta T. Right now, right now, right now. Write the whole thing. K equal 1 experimentally. Torque equals delta L over delta T. What is delta L? Final angular momentum minus initial. Angular momentum last week, final note, I found equation I omega. So I omega minus initial I omega naught. Take I common. Omega minus omega naught divided by time. That's delta omega divided by time. Delta omega is equal to what? Delta omega over T is what? Alpha. Angular acceleration. Angular acceleration. Right now, what is torque? Moment. Force multiplied by perpendicular distance to the pivot point. Sometimes they will give you a force couple. Remember, force coupled is also a torque. When you are driving, you are applying a force down on the steering wheel, up, so rotation. When you are opening the tap, how many fingers do you use? T. These two. Therefore, rotation. You are applying a couple. Force couple. I'll show you what a force couple is. Have you finished writing? Because sometimes they will give you force couple. Force couple and torque both are what? Same. But couple is slightly different in terms of definition. That you should know. Okay? Shh. Right, look. I hope you all wrote this. Right, look. Shh. If there are equal forces, look at the board, please. Final one. If there are equal forces acting in opposite directions, equal forces acting in opposite directions, different lines of action. Different lines of action. This distance is X. This distance is Y. Here anti-clockwise. Here anti-clockwise. Both are anti-clockwise. So here about O anti-clockwise if I take, force into perpendicular distance. anti-clockwise. Here, force into perpendicular distance. F is common, x plus y. This is called a couple. Why couple? You need a couple force. But they can't be along the same line. They should be in different lines. Look at the couple. Huh? One of the forces multiplied by the perpendicular distance between the forces. Steering wheel. 1, 2. Equal force. One force multiplied by perpendicular distance. These also a couple. Couple is also equal to the form of what? Torque. Don't forget. So couple is acting in the same direction. Example, steering wheel rotation. Example, tap opening every day. Here. Even the shower. Same. You're applying a couple. Check and see the knobs of the shower, what do you call, shower cup. One finger here, one finger here, there. You're rotating. You're applying force, what? Equal opposite. Equal opposite. Lines of action different. Couple means one of the forces multiplied by perpendicular distance. That is also another torque. You know, right there. In a force couple, in a force couple, two equal forces in a force couple, two equal forces whose lines of action are opposite. Whose lines of action are opposite. And not along the same line. And not along the same line. And not along the same line will create a force couple. Will create a force couple. This is also a torque. This is also a torque. As an example, rotating a steering wheel, rotating a steering wheel, rotating a steering wheel, comma, opening a tap, opening a tap, etc. We are applying force couples. We are applying force couples. We are applying force couples. You can show this. So right. So now next week work is this. I'll be introducing to you some equations, same as equations of motion, and then what we can start solving problems. Okay. Both are anti-clockwise. If common, one of the forces multiplied by the perpendicular distance. Okay, no? Right then. Don't forget this now. Torque equal I alpha. Okay, then enough for today. Get home safe.